Okay, so I think I'm recording now. Do you know, Fernanda, if I'm recording? I think so, right? Did you receive like a message saying, okay?
Yes.
Okay, so as I was saying, Pablo Lichtig is a biologist from the University of Buenos Aires, from the Faculty of Exact and Natural Sciences. He's doing his PhD at UNSAM in Argentina, with close ties to the Comisión Nacional de Energía Atómica, the National Committee or Commission of Atomic Energy. And he's presently doing a research stay at NCAR in the US. He is specializing in air quality studies in South America. I believe in South America, maybe in other places as well. But in any case, Pablo, thanks again for joining us, and the floor is yours.
Great, I'll share my screen. Oh, I need to get permission to share my screen. Just since it's recorded, I want to make it clear. I'm currently a postdoc in NCAR, even though I haven't finished my PhD, so I'm still kind of a little bit in both. I need permission to share my screen. Okay. Oh, it's because you are sharing. I think that you just need to stop sharing, and then I should be able to share.
Yeah, and now you're a co-host, so probably you can share your screen now.
So you should be seeing my screen now.
Yep.
Just give me a second. Can you see it full screen?
Yes.
Okay, so what I'm going to present today is work in progress. It's work that I have been doing with Nicolás Huneeus from the University of Chile. And I saw that today we have here Guy Brasseur, who is one of the PIs of this project. This project is the PAPILA project, which is prediction of air pollution in Latin America and the Caribbean, which aims to establish a sustained network of partners with complementary expertise to develop and implement an analysis and forecast system for air quality with downscaling capability for America Latina, for Latin America and the Caribbean region. The PIs of this project are Guy Brasseur from the Max Planck Institute for Meteorology and Nicolás Huneeus from the University of Chile, who was going to give this talk but was not available. So I'm here a little bit in his stead. This is quite a big project which has partners in a lot of different places, in a lot of different countries. You can see those in the map. You can see my mouse, can't you?
Yes.
Great. And this project paid for people traveling from Europe to South America and from South America to Europe for 1 to 12 months in each case. So during this project, for example, I was twice for 6 months working with Guy in Germany. It did not, however, fund travels among South American countries. So we were not able to travel, I don't know, myself to Chile or so on. Okay, there were 2 diagnostic modeling efforts. A first big one, which was done for January and July 2015. Already a preprint has been submitted. There is a paper which we already sent minor corrections of. This was led by Jorge Pachón and Marielo Paso. You can check it there. It has already been reviewed. It has already been resubmitted, and hopefully we will have it published soon. And there is a second effort, which is the experiment of 2019, where we simulated 3 months, January, July, and September. And this is still work in progress. That's being led by me and Nicolás Huneeus. I will focus mostly in this second experiment, although I will mention a little bit the 2015 experiment. Okay, just as a brief summary of the 2015 experiment, different models were used, which included CLAM, which is the Finnish model, the standard CAMS reanalysis, CHIMERE simulations, EMAP simulations, and 2 implementations of WorfCam. This was done for January and June. I think that most people there are probably Southern Hemisphere people, but just in case, January is summer, June is winter. And it was done at a resolution of 0.2 times 0.2 degrees, more or less. Each model had its own setup, but we tried to get as close to that as possible. And each model was set up independently. So there was no effort made to make each model look similar other than the resolution. This was done on purpose to have as big error bars as possible and to be able to really calculate an ensemble. It has advantages and disadvantages. We will discuss about that when we get to the next experiment. I will only go through a very short summary of all of this. We saw something we expected. Different models perform differently. Usually, however, the ensemble performs better than each model individually. I won't go into a lot of details, but the preprint is there, and I would really suggest that you go and read it if you're interested in this work. In terms of different months, we also see that models that perform better in January don't necessarily perform better in July, and models that perform better with one pollutant don't necessarily perform better with another pollutant. This is nothing new. This was expected, but it's also what we saw. Just one thing, this experiment was focused mostly, not mostly, exclusively on the surface layer, and mostly on cities. We got some conclusions and we learned some lessons during this study. One of the lessons is that there is a significant challenge because there is limited information on anthropogenic emissions, land use, and vegetation types. The anthropogenic emissions issue is being addressed. So the PAPILA project includes a group which is working with the emissions. Although the PAPILA project formally has finished, this group is still working with that. And there was already an inventory built for 2015, which has already been published. In spite of the relatively coarse resolution, most models could reproduce air quality observations in large cities, but the performance was a lot worse in smaller cities. As expected, there seems to be an inverse relation between NO2 and ozone biases. So if anyone has questions about that, we can discuss about that either later if we have time or offline. And there is a significant challenge in the lack of measurements in many cities in the Latin American region. So the cities that were analyzed were very limited, partially because not every city had enough measurements or enough measuring stations. After doing this experiment, we went for a second experiment, which we called X2019. This is still work in progress, as I said, so you will see that some things are still not completely rounded off, but I'm willing to discuss all of them. We did a couple of things differently. On one hand, we went for 3D data, not just surface analysis, because we thought, okay, since we like measurements, we can at least analyze what happens in remote areas with satellite data. And you do need 3D data for that. We did a different model setup, so the models that we used were different, depending on the availability of the modeling groups. And we also did some limited local regional refinement, which I will not discuss today. But for each city of these 4 cities, which are Santiago, Buenos Aires, Sao Paulo, and Bogota, we did one regionally refined simulation, usually done by the group that is working in that city. So I did the regionally refined simulation for Buenos Aires. The 2 groups working in Chile did it for Santiago. The group working in Sao Paulo did it for Sao Paulo, and so on. Well, and the group working in Bogota did it for Bogota. In terms of the setup, we simulated 3 months, January, July, and September. Why September? Because it was a high fire season during 2019 in the Amazon. So we thought we might see interesting results. And for this experiment, we tried to set up the models as similarly as possible, with the exception of the chemistry. So there are some smaller differences and some larger differences anyway. The first difference was an error in communication, honestly, which is that we didn't decide on a version of FIN 2.5, of the fire emission inventory. So I happen to use version 2.5 and the rest of the group use version 1.5. So there is a difference in the fire emissions, but the anthropogenic emissions are the same. Every model was forced with WRF meteorology, with the exception of one of them, which is Musica V0, because it can't, because it's a very different model that runs its own meteorology. All of them use the same biogenic emissions, and all of them differed in the chemistry. So most of the differences can be probably assigned to the chemistry and to the way to the model variability itself. That doesn't mean that we can necessarily say that one model is better than another, because since we forced all of this, maybe a model would perform better with a different anthropogenic emission inventory, or with a different biogenics, or with different meteorology. But at least it gives us a clue about model variability. Okay, some differences, I already mentioned this. So when no biomass burning was present, the differences should be mostly due to model variability, hopefully. Let's see some preliminary results. As I said, this is all work in progress, but feel free to comment on all of these or criticize it or whatever. I'm happy to go over that. We did some analysis on the surface over cities. And what we see is that the performance of the models differs strongly according to the period and the city. As an example, Buenos Aires during January seems to have very low modeled carbon monoxide and nitrogen monoxide, although nitrogen dioxide and PM10 perform well. There are no measurements from high quality research grade instruments for ozone and PM2.5 during this period in Buenos Aires, so I can only see how the models look, and they perform differently, but not too bad for the most part, in the sense that they are kind of similar. However, when we look at the same city for a different period, sorry, I didn't mention this, in every case, the blue line is the model mean, and the black line is the observations mean. This is always a city average of all of the measuring stations in the city. I should have mentioned that. What we see is that the performance is a lot better for July, which is not obvious. It's not obvious that this had to happen, but it did. We are still not sure why the performance changed so much from city to city. I'll make a small caveat about ozone here. This is only one station. Buenos Aires has few research grade stations, and it had even fewer during 2019. It has now 4. At the time, it had 3. And we set up a different one in CNEA, which was not there during January. So ozone is only one station. So take this plot with a grain of salt. Okay, when we look at Sao Paulo, we see that the stations have huge variability. Just in case, the gray line, the gray area is the station range. There's the range of the measurements. The models, since they were run with a coarse resolution, do not really capture that. You don't see that in this figure, because this figure has only the model mean and model median, but did not capture the spatial variability, but performed mostly okay when it comes to the mean. Not always, but for the most part. However, in some cities, some of them with very complex topography, like Bogota, we had some issues, and especially there are huge issues for ozone. I was discussing this with Guy yesterday. He was here. And we are also surprised by the fact that ozone looks very low in the measurements. So we need to understand what's going on, whether the models are overestimating or underestimating something, whether the measurements have some problem. We still don't know. We have to find out. This is surprising, especially considering that NO2 is not overestimated. Due to the chemistry of NO2 and ozone, when we have polluted cities, which is mostly every big city, and we are analyzing big cities, is that you would expect to have an opposite bias. So you'd expect that if ozone is too high, then NO2 is really too low. And this is slightly low, but not very low, and so on. So this requires further research. CO is underestimated. Once again, it's not surprising. We do see biases with CO normally across the world, especially in the Northern Hemisphere, but it's still something to take into account. When we look at very complex cities like Santiago, we have huge problems to represent that. So Santiago has a very complex topography. It's not as big in terms of area, and the models have huge trouble to reproduce that. Surprisingly, CHIMERE, especially with CO, is a lot more different from the other models than what we would see, which actually makes the mean look better because the other models were too low and CHIMERE is too high, but it's still more different than I would have expected. Some pollutants, though, like PM2.5 and NO2, perform all right. I still need to look at the fact at whether the high resolution implementation of CHIMERE and the MEP, which were the two models run in Chile, might show better performance. It might, because it's probably able to represent the topography a lot better. However, it's still forced with the same methodology. CHIMERE and MEP are two offline models, so it might also not perform better. I still haven't really analyzed that as much as I wanted. Okay, I wanted to also show some of the comparisons with satellites. I will only show a few examples, and I will mention the rest just for the sake of time. When we look at CO, we see two overestimation areas that are consistent across models and across periods. One which is here in the region of the Altiplano, part of the Amazon, and one which is in the La Plata Basin. These two regions are overestimated in every model for every period, which is interesting. For the Amazon, or for the region close to the Amazon, right here, I think that has probably to do with biomass burning emissions. Although a previous study, which was also done kind of inside of PAPILA, which I will show at the end of the presentation, just a link to, has also estimated that a lot of the CO here is secondary due to biogenic VOCs. Over the La Plata Basin, the truth is I don't know what's going on. I don't know why, but every single model is overestimating it. Since every single model is doing that, I would think it probably has to do with emissions, but it might be something else, which I don't know. I wanted to also show an example during the biomass burning season, during September, for Tropomi column NO2. There are biases, especially during the biomass burning season, but those are not consistent across models. So, for example, the first two models use the same biomass burning emissions, which are lower, but they are overestimating NO2, according to Tropomi in the Amazon, whereas Musica V0 use FIN 2.5, which has higher NO2 emissions due to biomass burning. However, it is underestimating it over this region, which is not exactly the Amazon, it's farther south, but also over the Amazon. So this is due to model variability, and it's an interesting topic to go into research. Since NO2 has a short lifetime, this is probably mostly chemistry and chemical reactions, which is slightly surprising because I won't go into a lot of detail for that, but for the gas phase, these two models, so the WRF-Chem version running by the University of Sao Paulo and Musica, for the gas phase, they have very similar chemistries, but the aerosol is different. Okay, we were also concerned with aerosol, which is one of the main pollutants in South America. And I just wanted to show one short example during January 2019. And what we saw here is that Musica V0 has a huge overestimation in the region of Peninsula Valdez. This seems to have to do with the dust scheme. So it seems to be forcing too much aerosol over the region of the Valdez Peninsula. And there are people working in the dust scheme in Musica V0, so this might be fixed by the next version. In the beginning, I actually thought this was really true. When I ran an old version of WorfChem, I also saw something like this. However, the satellites do not detect it. And it's so big that if the satellites do not detect it, it's probably not really there, especially for AOD, which can be measured pretty well from space. Also, the other models don't detect it. There is also an overestimation region in northern South America, which most models have, but not all. For example, IMEP doesn't, which could be a topic of future research, but it's not a huge overestimation. It's smaller. And it seems that I went way too fast because I'm about to finish, and I thought this was going to take a lot longer. So there are partial conclusions and to-dos. The first partial conclusion, different models are different. This is not something new. However, there are consistent biases that show uncertainties that need to be addressed. One of them is fires. When you look at the fire inventories, you look at FIN 2.5 and FIN 1.5, and you compare it with GFAS, QFED, and so on, you see huge differences. And when I say huge, I mean one might be 3 times the other. So those are really, really big. We need to address that. All of these are derived from satellite and often even from the same satellite instruments. They are just different products, and yet the differences are really, really large. When we look at the anthropogenic emissions, when we look at the efforts done by PAPILA itself, which I have not shown today and have not been used in the simulations, we also see big differences with CAMs. So just as an example, when I looked at it over Argentina, NOx over Argentina was only about half in CAMs than it was in the PAPILA inventory, but VOCs were a lot higher in CAMs than they are in the PAPILA inventory. So we need to address that. We need to make a really concerted effort to understand what's going on. The land cover is also not well characterized. There are lots of experiments over the Amazon, but the rest of Latin America and especially of South America, which is what we focused on in the second experiment, is kind of not really known that well. The Andes are still likely problematic at 27-kilometer resolution. We need to go to higher resolutions to be able to resolve all of the complex topography there. However, a simpler topography like Buenos Aires, which is flat and has moderate winds all year round, and its air gets completely renewed every day, did not necessarily perform better. So we saw that in January, we had huge biases over Buenos Aires, which was very surprising to me, even though in June, we saw good performance. And the performance might vary considerably depending on the period analyzed, which is not that surprising, but yeah. So there are a few to-dos that I still want to look at. One of them is adding vertical profiles over the cities and maybe also in remote areas, which would just be useful to compare models to themselves. We don't have measurements. We do have some satellite vertical profiles for CO, and we do have some ozone zones over Quito, although I don't think that the period matches exactly. So, but at least we would know how the models differ from each other. We need to analyze the effects of different resolutions over model performance. I'm not convinced that it's always necessarily better, but probably in regions with complex topography like Santiago, we really need to go for that. And when you look at the modeling system that Chile has, they go for very high resolution and they go for simple chemistry. So they pay the price to use simple chemistry to go to high resolution. And they get pretty good consistent results. And then we need to go into a real deep dive into the model biases. Why are some model biases consistent across models? If they are consistent across models, then something is wrong, either in the emissions or in what we know about those regions. I wanted to briefly mention two miscellaneous papers that are also done kind of in the framework of PAPILA. One which was a study done over addressing the air quality changes during COVID in Buenos Aires, which took into account the changes in traffic, which is useful also for the emissions and for the effects. And one which was a multi-scale CO budget estimate across South America, which was the same simulation using Musica that we are using now for PAPILA, and it was a simulation done in the framework of PAPILA with some tweaks here and there to be able to do this analysis. I wanted to mention a little bit of the institutes. As I said, these are a lot of different institutes across Latin America and across Europe. Sadly, for Mexico and Brazil, although they still worked really hard, they couldn't get travel funds due to some limitations on how the project works, but they still were part of it and they still worked on this project. And especially I wanted to thank the PIs who are Nicolás Huneeus, who is not here, and Guy Brasseur, who I think was here at least. I don't know if he's still here because I can't see who is here, but he was here until very recently. And then I'm open to questions. I'm sorry it took so short. I miscalculated.
All right, thank you very much, Pablo. Let's make a applause for you. So yes, you explained it very shortly, a lot of work. This, what you showed to us is a huge work that you have done in this project. So I would like to ask to everybody to leave your questions in the chat and I'll be reading. So Pablo, let's go with the first question you have. It is PM 2.5 refers to what aerosol types? Biomass burning, also dust, anthropogenic? I think that question came when you were showing the results of modeling versus observations in the cities.
Yes, so PM 2.5 is the complete PM characterization that the model does. So it's particulate matter with an aerodynamic radius smaller than 2.5 micrometers. And most models have a product which is total PM 2.5, and this usually is also measured as total PM 2.5 in the cities. So most of the instruments that we have, like regulatory instruments, measure total PM 2.5. The models have some chemical characterization, which I have not gone into, but you can distinguish usually sea salt from dust, from black carbon, from maybe some other categories, depending on the model. Guy raised his hand and he's the model expert. So if that's okay, he might give some useful insight.
Yeah, he just raised his hand and also Fabrice. So please, can you answer? Guy?
Okay, well, yeah, I'm still there, Pablo. Yeah, so thank you very much for your very nice presentation. I have a question about something that you didn't really discuss, and that's the way the models, the different models, reproduce the boundary layer. A lot of the differences in the calculated value could be related to the fact that the boundary layer is higher or lower depending on the model and so on. I'm thinking in particular about Santiago, which is surrounded by mountains and so on. And so the boundary layer might be very special in between the mountains, keeping the pollution really top down on the city. So have you looked a bit at the way the boundary layers are treated by those different models?
Yes, so we have the boundary layer in the output, but that's still work in progress. So I wouldn't be confident on giving you a finite answer. The boundary layer does differ a bit. In most places, I didn't didn't seem to be huge, but I still have to look at it in a little bit more detail. Look at it like during the diurnal cycle of the boundary layer, whether it's collapsing during the night, which it might be. And I haven't really looked at that yet. So that's still something that definitely needs to be done.
All right, thank you. Maybe I would like to ask to Fabrice if you wanted to answer anything or comment anything about the PM 2.5 type.
Hi, no, I'm just too lazy to type my question. I'll just go to the back of the list and I will ask it in person if that's okay. Thank you very much.
So I would like to ask to Pablo if that you comment about PM 2.5 is quite the same answer for PM10.
It is. Of the models, there is one model, which is Musica, that doesn't have a PM10 product. So that is not here. It's not included. But the rest of the models is a total PM 2.5 product that they have, and the measurements are pretty much the same. This depends on how PM is measured, but it's measured constantly and it's measured at total mass.
All right. So we have another question from Santiago that says, when comparing with MODIS sensor, is the model data sampled at the same time when the satellite observation was made? In other words,
Yes.
Are the satellite and model comparison done in the same time window?
Yes, but not exactly. So what we did is MODIS passes mostly during noon. And what we did is we took a time window of 2 hours to noon. So it was 3 hours in total, surrounding noon, local time for each one. So yes, but not exactly the passing time, rather an average of a couple of hours surrounding it, but this was not a whole day. So what we did is we just made everything else. We just discarded all of the other values and we calculated the monthly mean of that.
All right. So I have another question from Juan Cuesta. It is possible to know in which of the cities analyzed there is a contribution of local pollution and long-range transport, or local pollution only?
It's not always easy. Sometimes you can see it in the model. This study that I mentioned here does that using CO tags, but that's easier to do with that model because that's a global model that has only regional refinement. I didn't go into detail of how the different models work, but Musica, which is the model that is the most different from all of the others, is a global model where you just zoom in into a region. So the grid is not the same, it's not uniform all over, but you rather zoom in. And for this, we used like we used tagged tracers, CO tag tracers. And what we saw is that at least for CO, which is usually the easiest to analyze because it has a long lifetime and the chemistry is not that complicated, even though the models do have big biases. What we saw is that there is a large influx of pollution from biomass burning in Central Africa. However, the local part is still most, but we could get something that could even be 20% of the total CO coming from biomass burning in Central Africa. Just so that we don't get too conceited in when we look at the southern tip of Africa, then we are sending a lot of pollution to them. So, yeah. I'm not sure if that answered the question, but.
Yes, thank you. Yeah, and concerning the vertical distribution, and these fires from Africa, do they come in the free troposphere or they mix down to the surface? How does it work?
They do mix down. A lot of it is not that low, so a lot of it you see it over 800 hectopascals or over 700 hectopascals, but it's still not that high. So you're not talking about 200 hectopascals. You're talking about 700, 600. So some of it does come into the surface. However, it's true that probably a lot of that is not detected in the surface measurements that I showed.
Okay, thank you.
All right, Fabrice, your turn.
Thank you, and thank you for allowing me to bend the rules a bit here. I have a question about, I mean, you mentioned that the models are different, right? Okay, so that's fine. But then if you simplify the topography, it doesn't really improve things. So my question here is, okay, so what do you think is the problem here if it's not topography? What could we do then to try to improve model performance? What is the root cause here? Because obviously there's a problem, and if it's not topography, is there a problem with the models themselves, or do you think it's something in the boundary conditions or something that is causing the problem? Where is the problem? That's my question here.
Yeah. I'm not convinced that topography is not part of the problem. I'm convinced that it's not the only problem, because otherwise we would see Buenos Aires would perform great and Santiago would always be rubbish. And that's not what we see. I think there are lots of model uncertainties in here. One of them is, of course, the chemistry, but I think that a lot of it has to do with the fact that we don't have a good characterization of the emissions. We don't really know the land cover all that well. When it comes to biomass burning and VOCs, that's really important. And then when we look at the different anthropogenic emission inventories, they differ a lot. They differ greatly. And then, of course, the Andes are hard to model, and this has an effect over all of the continent and not just over the Andes, because we have a lot of transport between different parts. There might be other sources of uncertainty that I'm not sure about, but I think that we need to address the uncertainty in the emissions, and we need to address how the models have been tuned. A lot of the models have been tuned very much in the Northern Hemisphere, especially in the US and Europe. And some of them have, some magic numbers that are retuning some things. And those magic numbers might not work for South America. So I think it's probably a little bit of all of that. But I wouldn't say that topography is not the issue. I would say it's not the only issue.
Right. So, I mean, Guy, did you want to?
Yeah, I just wanted to add something to what Pablo responded. When we started in Europe or in North America to do model intercomparison, the models were giving results everywhere. There's a lot of dispersion between the models. And it has been a long way to understand exactly what were the different problems. And the problems were everywhere. So the way we treated meteorology, the way we treated boundary layer, the way we treated the emissions, the different types of emissions, and so on. And so I think probably there is not one cause. There is a lot of different reasons for that, including, by the way, the observations. Because, for example, when in Bogota you have 10 ppb of ozone, which is very low, and you don't have a very high NOx, so it's not a titration problem, you can ask yourself, why is that, independently of the models? What makes the ozone to be so low when the NOx is a bit higher maybe than ozone? So there is a bit of titration, but not very, very much. So I think there is a long way to go to address a lot of the different issues, including the emissions. So I would really start by looking very much at the meteorology, see how if the meteorology for which we have good data usually is well represented by the models. At the same time, I would really work on the emissions, and not only the anthropogenic emissions, but also the natural emissions. And what is emitted in Bogota, in Santiago, it's not very clear. People do emission inventory on a very, it's very few data. They interact, they connect it with the economy, with a few indicators, but it's very, very uncertain. So there is a long way to go, and I think it is very nice that this first step, intercomparison, has been done because it reveals essentially a kind of a way forward in terms of work to be done in the different cities of South America. And things will improve gradually, and there will be a lot of fixes in the models as time evolves.
Right. Thank you. So basically, I mean, there are two things here. One is like the data that we provide the model, and the second part is how the models work. But I feel like there is a major problem in our understanding of the processes. The models just are not complete. They're not good enough yet. So I think, yes, we can try to improve emission input and all of that, but while we don't have a good understanding of the processes, and this is not included well in the models, we will always have this dispersion between the results. So there is, I think that, yeah, there is a very big effort to be made here to try to improve our understanding of the processes as well as the input data. Thank you.
Yeah, and it's true, just going a little bit over that, it's true that even though the models have the same emissions, they are still really different, which shows that the emissions are not the only sources of uncertainty here. I think that they are probably the main one when you see all of the models fail the exact same way, which you sometimes see. When all of the models fail the exact same way, then I'm pretty confident that the emissions have something to do with it, although they might not have, and we just might have the wrong process in all of the models for something. When they're all over the place, which you would see like, if you give me 1 second, you would see like here for NO over Buenos Aires, they're all over the place, then it's probably not the emissions. If it was the emissions, we would see all of the models fail similarly. Here, we probably, yeah, these numbers look wrong. I have to check this. Here, we probably have real differences. Real uncertainties, real model variability. Yeah.
So, for example, you underestimate here in Sao Paulo the peaks.
Yeah.
Peaks, for example, in NO and NO2, and that is probably a meteorological signature that, you know, the boundary layer is very more stable or something like that, and that the emissions stay confined very close to the surface. So it's a lot of processes that needs to be investigated, and some might not be well reproduced for different reasons. So as Fabrice said, I mean, one has to understand what's happening if we want to model it very well.
Yeah.
All right, thank you. This your comments are so very welcome because, of course, we are discussing how modeling can be improved. Now that it's also this reality that we are also comparing these chemical transport models to artificial intelligence results, so which I am I'm struggling with that, but it's really, really nice to try to understand the causes of all this. I would like to ask you, Pablo, which do you think are the most important differences between the PAPILA emission inventory and CHIMS? In the last seminar, we had a presentation from Enrique Pugliafito that he presented also some results contrasting PAPILA and EDGAR emissions.
Yeah. Well, CHIMS is very similar to EDGAR. So in that sense, it's not that different because what the CHIMS people do is they take EDGAR and they apply the Z strands with a specific with some specific mathematical techniques. So it's heavily based on EDGAR. So in that sense, it's very similar. What I think has the largest effect in chemistry, at least, which is what I'm mostly concerned with, is the fact that NOx and VOCs are very different between the PAPILA inventory and ChimSur, which is the one I really looked at. So as I said, the PAPILA inventory, at least for Argentina, which is what I mostly looked at, the PAPILA inventory has a lot higher NOx and a lot lower VOCs. That changes the ozone regime. So ozone will behave very differently in both cases. And then the models which we run using the ChimSur inventory are going to assume one regime, whereas if we had done the same with the PAPILA inventory, they might assume a different regime, like from VOC limited to NOx limited. So that needs to be addressed. I'm not sure that we have enough information to say which one has it right. You would normally assume that the one done in PAPILA is done using national inventory, so it's probably better. But, you know, we would need to, at least I think we would need to run a couple of more modeling studies using that inventory and see how well it reproduces measured concentrations. If we see a real improvement in the measured concentrations, that might be pretty good evidence that the PAPILA inventory is better, but this hasn't been done, at least not massively. It has been done shortly for the first PAPILA inventory. This is a paper which I should have maybe written the link, the DOI here, which was published by Paula Castesana et al. And I think it was led by Claire Gragnard. And they did some shorter simulations and they did see some significant improvements. So it is probably better, but this was an inventory which was only done for 2015. And I mean, in this last 9 to 10 years, things might have changed quite a bit.
Okay, thank you. So anybody else have a question for Pablo, maybe? No? So I would like, thank you very much, Pablo, again for your presentation. And I would like to invite you all to our next seminar. So please, Pablo, if you can stop sharing your screen, I will share mine. Thank you.
Yeah.
Nico, it's you. Okay. So, yeah. This is from our kickoff week that we are going to have in Buenos Aires from 2 to 6 September, Buenos Aires and Córdoba in Argentina. So these are the organizations that are involved in this network working. Just if you didn't have this information, maybe we can send it to you. You are all invited to join. It's going to be an in-person meeting, but we are going to have also a seminar that is going to be online too. So the first day that we have is on Monday. It's an intern working day within the project members. But from Tuesday to Friday is going to be open to everybody else. So this is the program for Tuesday. You can see these are going to be the presentations that we're going to have for Tuesday. And then for Wednesday, we're going to have a tutorial for learning how to use CHIMERE. So if anybody wants to join to that tutorial in person, we ask you to please let us know that you are interested in being there, because we're going to save you a space. And then we're going to have a seminar that is after lunch. That is modeling atmospheric pollution, recent advances with the CHIMERE model, that is going to be presented by Sylvain Mailler and Guy Brasseur. I don't know if I pronounced their names well. And then on Thursday, we're going to Córdoba, where we are. Here I am. And we're going to visit some places in the university and also have a seminar. And then the last day, on Friday, we're going to visit the National Space Agency, CONAE. And we're going to also do a visit to the neighboring mountains here. So you are all welcome to join to our kickoff week, ChimSur kickoff week. Please let us know if you're interested to join, and we're going to wait for you, welcome you very gladly. Okay, so does Nico, do you have anything else to say?
No, not really. Just to say that some of the activities of the kickoff will be online so that everybody can participate.
We are going to send you the details for connection to the seminar that I've mentioned for Wednesday. That is our third webinar, let's say, so you all can join. Okay, thank you very much to all, and let's meet the next time. Bye-bye.
Bye-bye.
Bye.